In this lecture, we will be learning about Taylor polynomial approximations. Let's remind ourselves the definition of a Taylor series. Given a function f with derivatives of all orders throughout some interval containing a, the Taylor series generated by f at x equals a is given here, and we see the first several terms written out. If we take a partial sum of that series, we call that a Taylor polynomial. So a Taylor polynomial of degree k, pk of x, is nothing more than that same formula for a Taylor series with infinity replaced by k. So we sum up the terms, stopping at the term where you have x minus a to the power k. Now we can use these as approximations to their generating functions. So Taylor's theorem tells us if we have f as before, derivatives of all orders on an interval containing a, then for each non-negative integer k, we can say that the generating function f of x is equal to that kth degree Taylor polynomial plus an error term of order k. We don't know exactly what the error term is. After all, would we really make approximations if we always knew the exact answer? But we know the form of rk. So rk of x looks like this, and it appears almost the same to be the first term that we left out of our kth degree Taylor polynomial. Look at this last term in the Taylor polynomial. The term in the expression for rk is the same as this, with k changed to k plus 1, but this a is a c. We don't know what c is, a priori, but we know where it lives. It's between a and x. And we can use this structure in this theorem to approximate f of x. So again, we're going to say that that kth degree Taylor polynomial is going to be our approximation to f of x. This comes up in many applications. In mathematics, science, engineering, in all sorts of settings, we find ourselves approximating functions with polynomials, Taylor polynomials. Think a first-degree Taylor polynomial is a linear function. It's often very convenient to have a linear approximation to f of x. If k is 2, we have a quadratic approximation. But an approximation is only any good if you can say something about the error. And that's the true power of this theorem. So let's look at the types of problems that we work with dealing with approximations. So we can use that Taylor polynomial as the approximation for f on an interval I with some error tolerance. And the key thing to recognize here is there are 3 different items in this theorem. First, we have the approximation itself. Then we have the interval I. And finally, the error tolerance. In standard questions involving Taylor polynomial approximations involve typically situations where you're given 2 of these and you find the third. So we will do 2 examples in this lecture where we're given the first 2, the approximation and the interval on which we will use it, and then we have to find what the error is, or bound the error. We want to find the error tolerance. So for example, suppose we are approximating e to the x using the 4th degree Maclaurin polynomial on the interval minus 1, 1. Let's bound the error of the approximation. And this is all based on the idea of finding the worst case for the error. You can never be worse than the worst case. So the worst case for the error is your bound. Recall this was our Maclaurin series for e to the x. We note if we're using the 4th degree Maclaurin polynomial, then we are using the sum of the terms up to the degree 4 term for x. So now let's think about what Taylor's theorem says. Taylor's theorem tells us that f of x in this case e to the x, is equal to p4 of x plus r4 of x, where r4 will look like the first term left out. So we will have the fifth derivative of f evaluated at c over 5 factorial times x to the fifth. And what we care about is bounding this. So it's important to recognize, again, if we rearrange this equation, r4 of x is e to the x minus p4 of x, which is why we think of it as the error of our approximation. It's the real thing, the goal, minus the approximation to it. So we have a form for our r4, and we know this holds for some c between a, and remember, if we're working with a Maclaurin series, that means a equals 0. So between 0 and x. Now, we also note 0 is the midpoint of this minus 1, 1 interval. If we were approximating on a different interval, the Maclaurin series wouldn't make sense. You want 0 to be in the interval. You want the a to be in the interval. So, let's take a look at trying to bound the absolute value of this error term. So the absolute value of r4 of x is the absolute value of this fifth derivative of f evaluated at c over 5 factorial times x to the fifth. Now let's look over here as an aside and recall that if f of x is e to the x, then any derivative of f of x is equal to e to the x. This means that our fifth derivative of f evaluated at c is equal to e to the c. So we have e to the c over 5 factorial x to the fifth. Now we also note e to the c, that's a positive number. 5 factorial is a positive number. Those can come out of the absolute value sign. And we're left with the absolute value of x to the fifth, which we could also write as e to the c over 5 factorial times the absolute value of x raised to the fifth power. And if we want to make things a little bit easier on ourselves numerically, we know that e is pretty close to but less than 3. So why don't we note that this is less than or equal to 3 to the c over 5 factorial times the absolute value of x to the fifth. And this is bigger than the size of our error. So with this expression for our error, our question is, what is the worst case for this? What's the biggest this can be? Well, recall that we're using x in the interval minus 1 to 1. We now have a function of x, actually equal to our error, that we want to bound. We already noted that e to the c will be less than 3 to the c. And so the question becomes, since 3 to the c over 5 factorial is a constant, what's the worst absolute value of x to the fifth can be? Well, let's think about absolute value of x to the fifth. That looks like x to the fifth with its mirror image about the y-axis over here. And we know that this achieves a maximum value on the interval minus 1 to 1 of 1. So this upper bound we have for our error has to be less than or equal to 3 to the c over 5 factorial times 1. We're almost there. Again, we don't know c, but the key was we know where c lives. So recall that c is between 0 and x. But we're working on the interval minus 1, 1. Wherever c is, it's somewhere in this interval, which means it also is between -1 and 1. What's the largest 3 to the c could be? Well, we know the largest this would be is if c is equal to 1. So if you think of the graph, if you think of having a c-axis and you looked at the graph of y equals 3 to the c, that's an exponential. It's strictly increasing. So if we're looking on the interval -1 to 1, its maximum would happen here at 1. And this, we can write out some of that factorial. 5 times 4 times 3 times 2 times 1. The 3's cancel, and we see that this expression is equal to 1 over, we have 5 times 4 is 20 times 2 is 40. So we know when we use this 4th degree Maclaurin polynomial to approximate e to the x, the worst possible case for our error is 1 over 40. Which means for any x, the error is at worst 1 over 40. So this is a very standard type of example to get a bound for the error of a Taylor polynomial approximation to its generating function. Let's look at another example. Suppose we want to approximate sine of x using the 7th degree Maclaurin polynomial on the interval minus 2, 2, and again we want to bound the error of the approximation. So if we do this, our polynomial goes out to the 7th degree term, and so we'll call that P7 of x. Now, we can take the approach of using Taylor's theorem again, and note that Taylor's theorem tells us that sine of x is equal to that P7 of x plus its corresponding remainder term, where r sub 7 of x looks like the first term omitted. So we would have the 7th, or rather the 8th derivative of f evaluated at c over 8 factorial times x minus a. Again, we're working with a Maclaurin series, so a is 0 to the 8th. And we can go through the same procedure that we just did. However, there is a very specific trait that this Taylor series has that the Taylor series in the previous example did not. And it is that this is an alternating series. Notice we go signs of plus, minus, plus, minus, plus, minus. And when we have an alternating series, we have an easier route than using Taylor's theorem. And we have to think back to our studies of alternating series and recall our alternating series estimation theorem. And remember, the alternating series estimation theorem tells us if you want to approximate an alternating series with a partial sum, the error of your approximation is less than or equal to the absolute value of the first term omitted. In this case, we were using the 7th degree Taylor polynomial, and our first omitted term is x to the 9th over 9 factorial. So what we can do in this case is say, what's the worst case for this x to the 9th over 9 factorial? All cases, we have this error being less than or equal to this term. Let's find that worst case. Well, we know, recall, our interval was minus 2, 2. So we're working with x in minus 2, 2. So this term, we can write it as 1 over 9 factorial times the absolute value of x to the 9th. And the absolute value of x to the 9th will look like our previous graph. And if we're working on minus 2 to 2, again, our maximum occurs at the endpoints 2 and minus 2. So we know that this is less than or equal to 1 over 9 factorial times the absolute value of 2 raised to the 9th power. This simplifies to 2 to the 9th will be 512, and 9 factorial is 362, 880. And this is approximately 0.0014. And so we see that this 7th degree Maclaurin polynomial gives us an error at worst 0.0014 when we're choosing x from the interval minus 2 to 2. The thing to really keep in mind about this approach is that it's easier than using Taylor's theorem because the c term does not appear. You can just look at that first term you leave out, which means you only have to deal with x. Further, if you note in this question, if we had used Taylor's theorem would have us using a term with 8 factorial. Here, because we're looking at the first term omitted, the first term omitted was this x to the 9th over 9 factorial. The 9 factorial in the denominator gives us a tighter error bound than the 8 factorial would have. So we actually also benefit by being able to get this tighter error bound by using the alternating series estimation theorem in this case. The general rule is if you can use the alternating series estimation theorem in these questions, you absolutely should. We will look at the other two types of questions in the next lecture, so part 2 of this lecture, where we will see how to handle questions where we're asked to find an appropriate approximating polynomial or to find the interval on which our approximation will work.